All right, thanks Lisa. Good afternoon. So my name is Neil Prophet. I'm going to present the Reynosa gas explosion. The main topics I'm going to cover are just to summarize the incident and also cover motivation about why you might perform consequence modeling. And then the main part of the presentation is setting up the incident in SuperChems. Okay, so the incident I'm going to recreate occurred on September 18th, 2012, and it happened in Reynosa, Mexico. It's a natural gas metering station that takes natural gas, separates the impurities out of the natural gas, and then compresses it and sends it on through the distribution system in Mexico. Typically about 900 million cubic feet per day and operating somewhere between 300 and 500 SIG. And it's 12 miles from the US border. So the pipeline ruptured, and I'm sure everyone's seen the video. If not, I'm going to play it in a couple of minutes. But one of the important things from us as safety practitioners is that we can see all the different outcomes that we typically model. Initially, you'll see shrapnel, you'll see the pressure wave develop, you'll then see the turbulent momentum jet, then you'll see the flash fire, and then you'll see the jet fire. So that's one of the things that makes it really interesting to model. It resulted in 31 fatalities and also major disruption to the gas supply network in Mexico. Okay. It's very unusual to see an incident like this captured on video as it occurs. But it does give us an opportunity to learn from it. The image here is looking at the site, and I was able to figure out where the two cameras were located when we watched the video occurring. And also the area in orange is where the jet fire happens to be. Okay, so I'm sure everyone has seen this. Has anyone not actually seen this video before? Okay, so just pay attention to where the incident starts. Also notice the porta cabins that the truck is just passing at the moment. And in the foreground, we've got the compressor shelter. Okay, because they're going to give us some perspective when we come to model the scenario. Okay, so we can see the cloud, it's a turbulent jet. We also saw the pressure wave which shook the camera. We then saw it propagate as a flash fire and then stabilize as a jet fire. And here you can also see shrapnel flying across the plant. Okay, so terrible incident. One thing that struck me as curious was it was difficult to find any incident descriptions or any details about the incident online. We searched English language, Spanish language websites, very little in the way of incident investigations and details. So that was one of the motivations behind researching it further. Now there's a number of reasons why you would conduct consequence modeling. EPA risk management plan, you need to do worst case release scenario plus alternative release scenarios. Now EPA provides you with AirMod as a free software tool. but it's intentionally conservative. So if you want to sharpen the pencil, you can use a more complex, more sophisticated dispersion model, and therefore your impact distances may not be as far. Or if you're doing facility siting, looking at the maximum credible events, or emergency planning, or it might be a PHA action item that you need to investigate further. Or in this case, incident investigation, trying to recreate an incident that's already occurred. So given the lack of available data about the incident, I thought it was a challenge to set it up in SuperChems. And so we'll walk through the different steps involved in setting up this incident. So we'll start with a file, and generate scenario, generate site, mixture, look at damage criteria, outcomes, and then generate the results. Okay, so some of this is pretty basic for those of you that are familiar with SuperChems. You would open up SuperChems, select New, and create the file name. Enter the file name and location. And then what we'll do is we'll go to the Define menu and select Scenario, and we'll create a scenario. In this case, I called it Reynosa Release. But in actuality, you'd end up creating multiple scenarios with different what-if variations to it, or different weather conditions to it. Okay, so we select New and name the scenario Reynosa Release. And then we want to define a site. So there's a number of different types of information we have to associate with our site. So first of all, we'll select New and name the site Reynosa. We want to figure out where this incident occurred. So we know it was in Reynosa in Mexico. So this is looking at Google Earth, where I did a search for Reynosa. And it took a bit of hunting around to actually find the facility, because there's quite a few different facilities in that area. Okay, but it happened to be in a suburb of Reynosa. And we can zoom in just to make sure we're looking at the right facility. And actually, Google Earth, they update the images from time to time. So this facility has changed since 2012. So I was able to use a historical imagery feature in Google Earth and go back to the image from 2012. So that's the site where the incident occurred. And we can zoom in and pull it into SuperChems. So some of the features, just to help us confirm we're looking at the correct site, the compressor shelter, the porta cabin, and the approximate release point. Okay. And the distance between the approximate release point and the compressor shelter is roughly about 500 feet. And that's roughly how long that jet fire happened to be. So that's what we're aiming to recreate, is a jet fire that is 500 feet long. Okay. And we can see where the different cameras were located. So this is camera 1. Looking towards the release. And then this is camera 2. Okay. So we're able to confirm we're looking at the right facility. So we can generate a map from Google Earth. We need to save it in either bitmap or Windows metafile format for SuperChems to use. And so that SuperChems can recognize it as a map. What we need to do is define the origin and the scale and the north direction. Okay. So to do that, we pull in the bitmap image and then go to sitemap menu, and you've got your set scale, set origin, and set north direction options in the drop down. Okay, so that's our image. And then in terms of meteorological data, we can either enter that data directly, or we have the option to import it from a database. So one example of importing meteorological data from a database would be the Samson data, which is collected by the EPA, and you can purchase it from NOAA, National Oceanic and Atmospheric Administration. And that data has hourly data for ambient pressure and temperature, humidity, wind direction, cloud cover, and solar radiation. And we want to have at least 5 years worth of data for an accurate representation of meteorological conditions. Okay, so we define our site, and then what we can do is select Process SAM metadata files, and we can pull in the Samson meteorological files. In this case, the nearest data set was in Brownsville, Texas. So, Lisa's hometown. There's data available for every airport in the US, and so we selected Brownsville, Texas. Okay. So you pull in the Samson meteorological data. SuperChems will create a text file, and it will create your site object with a windrows that represents the meteorological data that you've pulled in. And then what we can do is we can break it down into different stability classes. Stability is a way of how much mixing in the vertical layers of the atmosphere is going to take place, depending on incoming solar radiation and wind speed. So we can either group stability classes together, like in this case we grouped A and B together, and C and D together, and E, F, and G together. Okay. And then what we need to do is add surface roughness, how flat the terrain is, water temperature as well, because the Samson data wouldn't know those inputs. So we end up with several different weather conditions. Stability class A and B, think of that as a hot summer's day. There's a lot of mixing in the vertical layers of the atmosphere. Okay. So it predicts that occurs 2.3% of the time with an average wind speed of 2.87 meters per second. This is also very useful for doing QRAs because it's giving you probability that you're getting a particular meteorological data set. Or stability class C and D, D being neutral conditions, occurs 65.8% of the time, with an average wind speed of 5.16 meters per second. Or E, F, and G occurs 31.9% of the time, with an average wind speed of 2.64 meters per second. Okay, and we can analyze the data further. We've got graphs of ambient pressure, wind speed, ambient temperature, and humidity based over a 5-year plot. So it really gives us the ability to analyze the meteorological data very accurately. But we can also enter the data manually. It's common practice to use D5 or F2, D5 being most common and F2 being the worst case. Some meteorological parameters are more important than others. So some of the most important ones would be the wind speed, temperature, stability class, and surface roughness. And there is guidance out there helping you decide what Pascal stability class to use. And that's based on your surface wind speed and incoming solar radiation. Okay, so that's our site object, which incorporates the map and meteorological conditions. We also need to define our chemical mixture. So we go to Define and select Mixture. Okay, now we know this is typical natural gas composition. So in this case, we selected 95% methane, 4% ethane, 1% propane. And I mentioned earlier, the typical pressure was between 300 and 500 psig. For modeling purposes, selected 500 psig. We also want to define damage criteria. There's various different types of damage criteria. It could be toxic effects, thermal, overpressure, noise, and it's up to us to select which ones are relevant to us for this example. So in this case, we define the thermal damage criteria. We can either define it in terms of flux, or time-integrated flux, or fatality probability. So in this case, what we've done is we've set up 4 different values of radiation flux: 500, 1500, 2000, and 3000 BTUs per hour per feet squared. Okay. And that corresponds to the different API values, where 2000 BTUs per hour per feet squared is the maximum heat intensity that someone can cope with for about 30 seconds. Or 1500 BTUs per hour per feet squared is maximum heat intensity for 2 to 3 minutes. And that's based on someone wearing FRC. Okay, so having defined the input data, we can then proceed with the consequence modeling. So what we want to do first is define our discharge conditions, and then take that and feed it into a dispersion model, and then model the consequences. So for the discharge calculation, I used the ideal nozzle model, and then for dispersion, I used the vapor jet, and for the consequences, I used the gas flame jet and flare model. So for discharge coefficient, for the discharge calculation, I used the ideal nozzle. So you go to your flow menu and select ideal nozzle. And that's a very versatile model. It can handle supercritical, 2-phase, or subcooled flow. So we use it for a lot of applications. So some of the key inputs that I set up in the discharge calculation: initial temperature, 77 Fahrenheit, initial pressure, 500 psig, composition that I mentioned earlier, flow diameter, I estimated a 2-foot diameter pipe and discharge coefficient. And typically, if we're looking at a pipe break, we typically use about 0.62 for a discharge coefficient to allow for the fact that it's not going to be a perfect hole. It's going to have some raggedness to it. One of the nice things about the ideal nozzle model is it can determine flow phase for us. In this case, it's obviously a vapor phase. So we run the calculation, some of the key outputs from the ideal nozzle for this scenario: mass flow rate, discharge temperature, discharge pressure, and flow phase. And then there's an option in the objects window of the ideal nozzle model where we can create a stream at exit conditions. So if we select that, we can then export all the data to a stream. So we then go to define and select stream, and we've got our stream that's automatically created. So it's got our mass flow rate, our discharge temperature, discharge pressure, and phase. It's all automatically carried over. But what we need to do is we need to add a release angle, release elevation, and a release duration. So in this case, I selected 5 degrees above horizontal and about 1 meter elevation. Okay, and then if we go back to the scenario object, now what we're doing is we're tying it all together. We've got our site data, we've got our chemical mixture, we've got our stream, and we've got our damage criteria. So that's all our inputs. And the nice thing about this modeling it using the scenario like this is we can make use of the event trees function in the scenario. And there's a number of different event trees you can select. In our case, it was the gas or vapor release event tree. Okay. You can either choose individual models, or what we can do is we can go to the gas release event tree, and we can select our source. In our case, it's a scenario-defined stream, and then we can select source development, basically allowing our vapor to expand to atmospheric pressure, and then we can select the dispersion model, in this case, jet dispersion. And then we can select various outcomes from either flame jet or flare, vapor cloud fire, fireball, or vapor cloud explosion. In this case, I only selected the flame jet or flare to represent our jet fire. And the nice thing about using the event tree is once we've made our selections here, we can automate those calculations by applying the default scenario and then using the batch queue to run our calculation. Now, it's no big deal here where I'm only walking you through one scenario, but we typically use the batch queue to run dozens or hundreds of scenarios at a time. So we apply the default and then select the scenarios that we want to run in the batch queue. And then once it's completed running, we can go to results generation. So in this case, we're looking at the thermal effects, and it's rotated through 360 degrees. And we have our 4 different values that we've specified that correspond to the different values recommended by API 521. If we look at the side view of the jet fire, you can see here that the jet fire is roughly about 600 feet long. The dark red represents the actual jet fire itself, and then we have the different corresponding thermal radiation values. Oh, okay, so you can just see it here. Okay. And then we have the 4 different thermal damage criteria being reported as well. So this is looking at our jet fire from the side. So we can really visualize how far the impact zones go. We can do the same looking at the dispersion of the flammable gas. So we can see how far our cloud goes. And I think this is about the LFL here and half LFL down here. And we can also look at the flammable concentrations from the side as well. So you can see how far the cloud goes, and it's showing us 4 different values: the upper flammable limit, lower flammable limit, half LFL, and quarter LFL. Okay, so some conclusions. So I'm just showing you one particular set of calculations, but this really requires an iterative approach to get it right. You know, there's many other things we could tweak to accurately represent the scenario. You know, for example, the 2 main variables that I could see were the actual hole size and the release pressure. And we could drill deeper into the case study. We could look at the effect of releasing through a pipeline. So rather than using the ideal nozzle model, we could use the net flow and select pipes containing vapor model instead. That way we could account for the flow going through the piping. We could allow for the effect of depressurization, because we're seeing the really high rate of flow to begin with, but over time that flow rate will decrease. So in the dispersion model, we could perhaps use the Gaussian tough dynamic model to show how the effects will taper off as the system depressures. We could look at the effects of the shrapnel. In the explode menu, there's an option for vessel burst fragment trajectory. So we could use that to analyze how far do the fragments go. Or, given that this incident already occurred, we could back calculate. We could look at where the fragments ended up and back calculate to figure out what the system pressure was. So looking at this incident gives us a much better understanding of the hazardous outcomes in terms of dispersion distances, the release rate, you know, how much did we flow when that pipe initially burst. And the calculations showed that it's about 10 million pounds per hour. It also gives us an understanding of the thermal impact distances and where it would be affected. Also, it's worth bearing in mind, if this incident had occurred 12 miles north, i.e. on the US side of the border, things would be significantly different. I would imagine we would have public inquiries, we would have chemical safety board investigations, industry-wide recommendations, and codes and standards being updated. But as it stands, if you try and research this incident, you're not going to find a whole lot. So there is some further information that iMosaic can provide. I did publish a paper in 2017 at the Mary Keogh Corner Process Safety Symposium. And we recently turned it into a safety video that's available on PSTV. That concludes my presentation. We'll be happy to answer any questions.
They never came up with root cause analysis for this study, right? We just saw the video.
Yeah, when we did some research, there was speculation, but there was nothing that I've been able to find that reached concrete conclusions.
Yeah, for pipeline releases, if you're just worried about level and you're worried about thermal radiation, safe separation distance, roughly maybe 2,000 BTUs per hour per foot. There is a very simple correlation that you can use, which was established for methane, ethylene pipelines, whatever, with toxicity. Essentially, the distance in feet is equal by either 0.8 or 0.84 times the square root of the pressure, PSIG, d squared.
Okay.
So it's one simple formula. Somebody actually elegantly worked out flow rate, thermal radiation, and worked it out analytically. So you can show, people use this for separation distances for gas discharges from pipelines. So the distance is equal, let's call it 1. Distance is equal to the square root of P, and PSIG times d squared in inches. That will give you the distance. So you could work it out on the back of an envelope and work it backwards.
But then you wouldn't need SuperChems.
But I mean, if you're doing a quick calculation, I get it. But it's out there. I mean,
yeah. It'd be interesting to compare the back of the envelope calculation.
Try it.
Okay, I will.
Neil, you said you did this in a bad queue. Did you do all the other permutations of analysis? Did you do a vapor cloud explosion versus a jet?
Well, I should have been creating many different scenarios to represent each of these permutations, but in reality, I just tweaked my initial scenario.
You saw in the video, you see that vapor cloud, and it didn't light off right away.
Mm-hmm.
So I'm curious to see what that endpoint looks like in that first edition.
the rule of thumb, Dave, is that you use the first 30 seconds of flow of pipeline rupture to establish mass that would be involved in any vapor cloud explosion or the subsequent fireball. Okay? Because the flow rate from the pipeline is going to drop very drastically. So you're going to calculate the first 30 seconds of flow. Neil was just doing a quick peek. Once you do that, you can calculate the fireball damage, and you can calculate the overpressure damage from that deflagration, which obviously occurred because it was a delayed ignition. Right? Then you can use this calculation for dispersion to LFL to calculate the flash fire zone, because obviously everything that burned is toast. So that's flash fire zone, if you're in it, you get it. And then you get to the sustained flame jet. So we do that when we do QRAs. All of these things are calculated, assigned conditional probabilities, and we do thousands of these scenarios, permutations. I think he was just trying to show you the functionality.
All right, thank you.